Thank you, Jim. I have to start out by saying this is actually really scary for me because UC Santa Barbara is the home of so many breakthroughs in solid-state lighting, in gallium nitride materials, and devices. It's the home of Shuji Nakamura, who, as we all know, in the 1990s did stuff that directly led to everything that everybody in the community is doing. So this is very scary. And so I apologize right off the bat if I say things that you guys already know, dead cold. But hopefully maybe I'll say things with a slightly different twist. So it'll be maybe the facts, but organized in a different kind of story. So I'm going to talk about solid-state lighting, which again you guys know all about, with an emphasis on towards smart and ultra-efficient. I've been mostly talking about ultra-efficient the last few years, but suddenly I've gotten religion, and so now it's not just ultra-efficient, but it's smart. And what I'd like to do is talk first about what some of the characteristics might be of smart, ultra-efficient solid-state lighting, what some of the economic benefits might be. This is actually somewhat controversial in the energy economics field as a whole, as well as the Department of Energy and other places. And then some of the challenges associated with getting to smart and ultra-efficient. So let me start by saying maybe things that you guys already know, which is that, of course, solid-state lighting has come a long way, starting from fire at 10th percent efficiencies, incandescence at maybe a few percent efficiencies, gas discharge lamps at maybe 17 to 20% efficiencies. Now solid-state lighting, which in principle can be close to 100% efficient. And so, as Jim said, at this point there is no doubt solid-state lighting will win. It will be the dominant lighting source for almost every kind of light source in the future. The only question, in a way, is what will its final efficiency be? Will it be on the order of 50% efficiency, which is what the Department of Energy has long targeted as its so-called efficient lighting target? Will it be more like 70% or higher, which some of us call ultra-efficient lighting? Will it be actually, and this is sort of a tongue-in-cheek, will it be more than 100%? Not because we're going to go to low currents and harvest thermal energy, but because not just the creation of the light could be close to 100% efficiency, but the way in which you use the light. If you direct the light and use it in a more efficient way than you did before, then in some sense, in some funny sense, the effective efficiency can be greater than that, greater than 1, and that would be sort of the domain of smart lighting, where you're tailoring the spatial and temporal characteristics of the light. So again, what I'd like to do in this talk is sort of talk about what would be associated with solid-state lighting that really was ultra-efficient and smart. I have a long list of acknowledgments, and I'm just surrounded by wonderful colleagues at Sandia and other places. Okay, so let me start with characteristics. And again, I'm not going to say anything that you guys don't already know, but I like to think of there being two kinds of characteristics that would be associated with smart, ultra-efficient solid-state lighting. One is, of course, all electroluminescence. As you all know, white light, about 80% of white light is in the red and green. And there's a Stokes deficit of about 25% in getting from the blue to the red and the green. So you automatically take a 20% hit in overall efficiency if you don't have all electroluminescence. And so the first important characteristic is that. Of course, that's hard. As you all know, that there's this famous green, yellow, orange gap. But if we do care about ultra efficiency, then somehow we're going to have to find a way around that. And if you not just want ultra efficient, but you want smart, then of course all electroluminescence doesn't hurt you there either, because now you have full control over the lumen content at every one of the wavelengths. So if you want to do chromaticity control or any other kind of control, then that's also a good thing. Okay, the second thing, which is maybe a little more counterintuitive, and this is something that I've been talking about the last few years, at first to a pretty skeptical audience, maybe still a little bit skeptical, I don't know, and that is that the light maybe not should, but can be spiky. I might even go a little further and say should be spiky. And to see that here, I've drawn the spectral power densities of a bunch of different lamps along with the human eye response, so you can sort of see how they stack up against each other. And in the red, of course, is the incandescent lamp, which is a really broad, continuous spectrum extending way into the infrared where you can't see. So this is very inefficient. That's the worst lamp. The second worst lamp is actually the phosphor converted LED, which is here in black. You can see the blue LED peak, the green and red phosphor peaks, and it extends further out into the red than one would like. And so again, you lose efficiency because the human eye can't see out that far into the red. Surprisingly, the fluorescent lamp is actually not too bad. It's not perfect, but it's not bad. It has spikes, and in particular has this nice spike at around 615 nanometers or so, without too much down out into the deep red, where again the human eye can't see. So the fluorescent lamp is actually not too bad. But the best solid-state light, or the best light source of all, would be this spectrum in white, which is the 4 spikes: red, green, yellow. I'm sorry, blue, green, yellow, and red. These 4 spikes of light are spread broadly enough in spectrum to be able to give very good color rendering of objects in the world around us, and yet they're concentrated enough within the visible, the part of the spectrum that the human eye can see, to give relatively good luminous efficacy of radiation. So that is a little bit counterintuitive, so I thought maybe I would spend just a little bit of time talking about this spiky spectra thing, and first talk a little bit about high color rendering index, CRI, and then second talk a little bit about high luminous efficacy of radiation, or LER. Okay, so let me talk about CRI first. And actually, one could start out by asking the question, which I was asked, well, you have these 4 spiky spectra. How could that possibly be a good light source? It's missing all of the spectra in between the spikes. Surely that would be a really crummy light source. And you go through the color simulations, and you find that, at least by the classic color simulations that are out there, it should actually be a good source. But you never know. Maybe in the old days when they concocted these color simulation things, they didn't really know about spiky sources, so they weren't thinking about testing those things to the limit. So we decided we had to do the experiment. So we actually constructed a 4-color laser illuminant. It's probably the world's most expensive illuminant ever. But we didn't care. We just wanted to do the human factors, the human factor study. And we put that into one side of a sort of a side-by-side test. And on the other side, we had conventional light sources, really good references. And actually, on both sides, we had references. So we did sort of a double-blind test where sometimes there would be references on both sides. Sometimes there would be the 4-color laser one on, and the experimenter didn't know, and certainly the person who was being asked which scene they liked also didn't know. And then we put 2 side-by-side seeds. We just used different things, and in this case, we used fruit. And what we found was exactly what you see, actually. It was really hard to tell the difference between the scene that was illuminated by the 4-color laser illuminant and the scene that was illuminated by the regular light source. In fact, when we first saw that, we were quite amazed. You turn off any one of the sources, so you only have red, green, or blue, or you have yellow, red, and blue, or whatever. And the scene, of course, looks terrible because you're missing one of those spikes. But then you turn that one spike back on, the missing spike back on, and it looks just beautiful. It was just, for us, it was pretty amazing. And in fact, what you find is that the 4-color laser illuminant was actually better in the double-blind set, or preferred by this audience of young college students that we could find to take the test at University of New Mexico. They actually preferred this over the phosphor-converted neutral and cool white lights, and we found that it was virtually indistinguishable from the incandescent lamp reference source and the warm white solid-state lighting source. So we were quite amazed. So now one could ask, okay, why is this? And I think the answer is that most objects in the world around us actually have relatively broad, continuous reflectance spectra. It's a very rare object, like a diffraction grating or something that has a very, very spiky reflectance. And because of that, and so these fruits are examples of those things that have relatively broad reflection spectra. And if it does, then you really can't tell. It's only if you have an object that has a very sharp, spiky reflectance that you would be able to tell, because maybe you would be missing the particular color, you know, in the illuminance itself. Okay, so color rendering index, surprisingly, now I don't want to make it sound as if for every situation 4 laser lines might be enough for illumination. It could be that there are some scenes that are more sophisticated than this, these fruit bowls that have more nuance in color, and so you might need more. Who knows? Maybe you might need 5, or you might need 6. You know, but the point is that you don't need continuous. You can do well with spiky spectra. Okay, so now spiky spectra buy you something else. So this is luminous efficacy of radiation, LER, and these are spectral power density simulations done by Po Che Hung at Konica Minolta. And what he's basically done is varied the spectral power density for a given color temperature and a given color rendering index, and asked and tries to maximize luminous efficacy of radiation. So basically, what kind of spectra will give you the best luminous efficacy of radiation when you constrain yourselves to a certain CRI and a certain CCT. And it's unconstrained in the sense of the spectral power density can be anything. So he's just varying in some random way the spectral power density. And what he finds is that in order for maximum luminous efficacy of radiation always gives you spiky spectra. It could be that for the very highest color rendering index, like down here it's CRI of 99, which is almost as high as perfect, which is 100, you might need more spikes. But the highest luminous efficacy radius is always given by these spiky spectra, except for the very highest, where you finally end up having to have a continuous spectrum. But as many of you know, 99 is really, really good in terms of color rendering. Actually, 90 is already quite good, and most sources out there are sort of in the 80, 85 kind of range. Now, you could also ask, given a CRI and given a CCT and given the best spectral power density that gives you the best luminous efficacy of radiation, what is the maximum luminous efficacy of radiation? So here's a plot of what that maximum luminous efficacy of radiation is as a function of color temperature for various CRIs. And what you see is that there's always sort of this peak at sort of a moderate color temperature. And that kind of makes sense, because if you're at a very high color temperature, then your light is more in the blue, where the human eye is not very sensitive. But as you shift your color temperature lower, then you're shifting light from the blue to the green, where the human eye is more sensitive, so it peaks. And then at the lowest color temperatures, you're shifting light from the green further into the red, where the human eye, again, is not very sensitive, and so you get this peak. You get this fall off at the lower color temperatures. Of course, as you increase CRI, the peak also decreases. That makes sense, because as you're increasing CRI, you're basically shifting spectrum out in order to fill the spectrum out to do better in terms of rendering of colors that are further out into the fringe of the visible spectrum. And as you do that, you move into regions of the spectrum where the human eye is not as sensitive. And so as you go from 30 to 70, 90 to 100, the peak goes down a little bit. But it's surprising how good you can be. Even if you insist on a CRI of 90, which again is very good, you can get to luminous efficacies of radiation that are on the order of 400 lumens per watt, which is quite nice. Okay, so the point of the last 2 V-graphs is that spiky spectra are pretty good. In fact, maybe even desirable. I would go so far as to say they're desirable. Now, so that's sort of just in a sort of a broad way some of the characteristics that one would like out of smart, ultra-efficient lighting. So now here's something a little more controversial, which is, well, actually that might be controversial, but this is maybe even more controversial, which is that who cares? So why would you care about getting to smart and ultra-efficient? Ultra-efficient meaning really efficient, like getting as close to 100% efficiency as you could get. We know that the solid-state lighting industry, the companies that are making products and whatever, they're going to make a ton of money even if all you do is get to 50% efficiency, because gas discharge lamps, which are the best you have, are only at 20, at most sort of 25-ish% efficiency. So you can get to 50% efficiency at a low enough cost. You're already going to win a lot. You're going to displace conventional lights. Your company is going to make a lot of money. So the benefit to getting up to 100% or close to 100% for companies is not so obvious. Okay, but is there benefit sort of on a global macroeconomic level to getting to closer to 100% efficiency? And the answer is maybe or maybe not. I think we probably genuinely don't really know the answer. I have an opinion, but I think we genuinely don't know the answer. And so here are two different scenarios for why or why not getting to ultra efficiency might matter from a global economics point of view. Okay, so on the left side, there's a scenario where this is the classic scenario. This is the normal scenario that we would normally think about. This is a scenario where light is not considered a factor of production in the economy, and that consumption is saturated. Okay, so what that means is that if light is not a factor of production in the economy, that means that GDP doesn't really depend on light particularly. So if you make your efficiency of your lighting source bigger and bigger and bigger, GDP doesn't do much. It stays at, in this case, it was like a 2011 sort of calculation. So it stays at whatever it was in 2011. It was $60.5 trillion per year. That's the GDP of the world. And as you increase the efficiency of light, well, okay, we're saturated. We're not going to consume more light. So phi, which is consumption of light, petalumen hours per year, also stays flat. Doesn't really change much. So the real benefit to increasing your efficiency is that you're going to save energy. Okay, if your light consumption is fixed, it's staying the same as you increase efficiency, then, but your efficiency is increasing. Whoops. Sorry. it'll stop if. Then the main benefit is energy consumption is going to decrease. So this is petawatt hours per year, and what you see is, as you know, lighting consumes about 1/15 of all primary energy. So if you go from 10-15% efficiency, which is roughly what the sort of standard aggregate efficiency of lighting, conventional lighting is, all the way up to 100%, you're going to save about 1/15 of all primary energy. So you're going to go down from, let's say, 44.5 petawatt hours per year down to maybe 42 petawatt hours per year. That's a big savings. That's in dollars. That's like $285 billion.
Is that global or is that U.S.?
That's global. So that's the world. Yeah. So globally, it's a huge number. For the U.S., it's maybe a third or a fourth, of that. But it's a big number, $285 billion a year. But there's also diminishing returns. Okay. So if you've already gotten to, let's say, 90% efficiency, and now you're asking, well, okay, if I can get to 100%, how much of a difference is that going to be? Well, what you find is that there isn't that much. It's 35 terawatt hours per year. That's about $4.4 billion per year. I mean, it's not a small amount, but on the scale of things, it's relatively smaller, and it's not as obvious whether the research effort involved in getting from 90 to 100% would actually be worth getting to. What? Definitely worth it. Because the thermal management, yes, okay. So there's other issues that have to do with, yeah, okay. Right. But that wouldn't affect the energy and economics picture. That would be sort of more of a, it affects cost, it affects penetration, all that kind of, yeah. Okay, so there is this other scenario, which is really interesting. It's, what if light is an economic factor of production? And so consumption isn't saturated. And so this model is actually something that one might call its profit maximization in a so-called Cobb-Douglas economy. And so those of you who have taken economics, you kind of probably know what that means. Cobb-Douglas just means that there's a production function of this sort of funny sort. And then there's profit, which is production minus cost. And you're trying to maximize profit depending on what you're producing and how much it's costing. And little phi is per capita consumption of light. And so little phi is entering into the production function, basically. Okay, so this model is basically one in which light is something that we don't just consume because we're spoiled and we just want light to waste. But we're actually using light because it's making us productive. It's helping us do things that we couldn't do if we didn't have light. Now, in the early days when you don't have much light, I think there's probably not much argument that, okay, yeah, lighting is good because it allows you to work indoors and you couldn't work indoors before, or allows you to work at night and you couldn't work at night before. Probably where the controversy is now. Okay, now in the developed world especially, are we saturated for the first time ever, or are there going to be more uses for light that would continue to make us more productive if we consume more? But so anyway, this is the other extreme of assumption. This is that light is an economic factor of production. And if it is, then if you follow through this model sort of in a way blindly, what you find is that GDP, teradollars per year, does increase as efficiency increases. The consumption of light also increases as the efficiency increases. Basically, the cost of light is decreasing as efficiency is increasing because the dominant cost of light is the electricity that you burn. So actually energy. In fact, we're not winning in terms of the energy argument because GDP is increasing a little bit. Actually, the energy consumption of the economy is also increasing a little bit because lighting is only one part of GDP, and so this sort of model is a self-consistent model. So if GDP is increasing, all sorts of other things have to be consumed in order to cause GDP to increase, not just lighting. So actually energy consumption actually increases a little bit. So this is actually kind of scary. So the main benefit in this scenario isn't that we're going to reduce energy consumption. We don't. The main benefit is that GDP increases, because lighting, again, is a factor of production in the economy. In fact, it increases a huge amount. Again, following blindly through this model where lighting is an economic factor of production, it increases by something like $1.3 trillion if you get from 10, 15, 20% efficiency all the way up to 100% efficiency. So this is a much, much bigger number than any of these other numbers. Of course, there's also diminishing returns. So if you've already gotten to 90% and you're just asking, okay, how much more am I going to win by getting to 100%? There's not a $1.3 trillion, but there's still $65 billion per year, which is much, much bigger than these kinds of numbers, over here. So if you believed this side of the equation, you would say, there's a lot of benefit to increasing efficiency because lighting is a factor of production in the economy. It's going to make GDP bigger and by a lot. Even after you're already at 90%, getting to 100 is still going to make it a lot bigger. But if you believe this scenario, then you would say, it's probably not worth it. You're at 90%, who cares? Don't try for 100%. Even if you're at 50%, you might not even try for 100%. So one of the big questions, and I think it's unresolved, because we don't know what the future is going to be. But this slide sort of illustrates maybe this slide illustrates what it's been in the past. Okay, you can't really say anything about what it might be in the future, but it says what it has been in the past. So this is a plot of per capita consumption of light in petalumen hours per year. That's little phi, as a function of this funny quantity here. And you see there's a bunch of data points. There's a historical time series from the United Kingdom that goes back to 1700. There's a contemporary data series in the 2000-2005 sort of time frame. There's even this data point from 1999, which is the world not on grid electricity. As you may know, there's like 1 or 2 billion people who don't have grid electricity, and so they make use of kerosene lamps even now. And so this data point corresponds to that world or that population. Okay, so all these data plots are plotted. It's their consumption of light per capita, and then plotted against this funny quantity, beta, which is just a fitting parameter, times GDP of that country at that time, divided by cost of light. And if you choose as your units for GDP billions of dollars per year, and if you choose as your units for cost of light dollars per megalumen hour, what you find is that this thing has the same units, petalumen hours per year, as this x-axis has the same units as the y-axis. And if you choose as your fitting parameter beta of 0.0072, what you find is that the data points fall remarkably on a straight line with zero offset. So that's pretty amazing. What that says is two things. It says that when countries in the past, over the past 300 years, when they've gotten richer, okay, when their GDP has increased, they've increased their consumption of light. It also says that when light has gotten more efficient, the the technology has improved and the cost of light has decreased, we've also increased our consumption of light. Now, and in fact, this is exactly the dependence that you would expect if one follows through this Cobb-Douglas model. That's exactly the dependence that you would expect. You would expect this kind of dependence. So it's suggestive that in the past we've been in that Cobb-Douglas sort of light as a factor of production in the world. You can sort of see it graphically too. Here's the Korean Peninsula, 1992. This is a satellite photo of light, and you can see it's much better lit in 2008 than it was in 1992. North Korea hasn't changed too much. It actually might have even decreased a little bit. There's some parts that have gotten a little bit dimmer, but basically this is what has happened in the past. It's when a country gets wealthier, when technology improves, people consume more light. So again, the caveat is we don't know what would happen in the future. It could be that for the first time in human history, we are saturated, that this is actually all the light that you would ever need. And this is probably something like 500 lux or something. That's a sort of a normal office kind of environment. It could be. But it might not be also. It could be that we will find other uses for light. It could be that we actually would like our seminar rooms to be even brighter than they are now. Who knows? I mean, some of you may know that if you go outside on a cloudy day, which is quite comfortable, not a sunny day, but a cloudy day, the lumen per square meter, the lux level, is about factor 10 higher than it is indoors. So there's certainly room for, if that's something that you would want, is more light. There's certainly more room within the sort of human comfort level. Okay, so it could be that there's lots of benefits to getting from 50 to 100% to get to ultra-efficient lighting. It could be that there's even more benefit to getting to smart lighting, where again your effective efficiency is somehow more than 100% because you're using the light more efficiently. And this is actually the first time I've used this view graph. I actually think, for a while I wasn't so sure, but I actually am starting to really come around to the belief that smart lighting really is real. It's not just Kool-Aid that we're drinking. All the way from chromaticity control to the integration of illumination and displays to managing circadian rhythms for human health, well-being, and productivity. Agriculture is a emerging, really interesting application. Communication, light field mapping, which allows you to use light to sort of figure out what's in a room and where things are and how they're moving. I don't know that all of these applications will become real, but some of them I'm pretty sure will, and they will really sort of transform how we.
By light field mapping, do you mean GPS, or what do you mean by that?
No, it's like there's places like TI. They're doing these structured light things where you actually put these weird patterns on things, and then you look at reflected light, and you image. You image the scene, and depending on how far apart the stripes are, or how whatever, you can figure out where things are, and get their 3D texture and where they're moving and stuff like that. It's quite. And so if you want to know, well.
So like radar. It's almost like radar.
It's almost like radar, except better, maybe.
Except,
it's line of sight, though, so it's not as, yeah, right. I mean, of course, it's a big invasion of privacy, but, but, that hasn't stopped anyone from trying to figure out where you are yet. Okay, so I've kind of talked a little bit about some of the overarching characteristics of smart ultra-efficient lighting, and I've talked a little bit about what some of the economic benefits might be. It's a little controversial, but I believe they're there. Let me just mention some of the approaches that one might think about for getting to ultra-efficient and smart. And at a device level, and now this is something that Jim mentioned at the very beginning. I am a fan of lasers, and so here I show sort of two approaches, and these are plots of power density into the chip, whatever that chip is. For LEDs, that's this thing in red, and then for lasers, that's this thing in blue. And and the 4 plots are: one is efficiency of the thing, of the chip, of the light emitting device. Another is the areal cost, the chip areal cost, and I'll explain that in just a minute. Another is the heat sink limited chip area, and another is the heat sink limited white light flux that you might get from that heat sink limited chip area. Okay, so let's start with efficiency. And so, as you all know, for an LED, you can't drive it very hard before you start to suffer efficiency droop. And it's not more than maybe a few watts per square centimeter. You know, there's been some improvements, but you know, it's still sort of on that order. On the flip side, if you drive a laser less hard than kilowatts per square centimeter, you don't even get lasing. And so there's this. We're starting to call this the valley of droop. You think of droop as, it's the valley of death. You think of droop as being just coming from the left side and moving to the right, and it's drooping. But actually, in some weird way, if you consider both light sources on equal footing, they both die in the middle. And so there's this valley of droop. Now, it could be that this valley of droop will get fixed, and that somewhere maybe the LED will improve, and we'll figure out how to fix that droop. But if it doesn't, then that drives you in 2 different directions. It drives you for the LED if you care about ultra efficiency. Okay, so you may not. You may say, oh, okay, I'm willing to live with less efficiency. I'm going to drive it harder so I can make the chip less costly per lumen of light that I get out. But if you care about ultra efficiency, that drives you to move to the left. It drives you to move to the peak, wherever that peak is, and that might be, let's say, a few watts per square centimeter. Okay, but that's such a low input power density that the chip areal cost actually also has to be low. And so if you just make this sort of naive assumption that, let's say in the limiting case, let's say your cost of light, the capital cost of light, is similar to what it is for traditional lights. Okay, so for traditional lights, the capital cost of light is about 1/6 of the operating cost of light. That is to say, if you buy a lamp and then you turn it on and use it for its entire life, and you add up the electricity cost versus the cost to buy the lamp itself, the bulb itself, what you find is the electricity cost is dominant. It's about a factor of 5 or 6 bigger than the cost of the lamp. So the capital cost of the thing that you buy is about a 1/6. So if you make that assumption that in the end game, that's about where lighting is going to end up being, where the dominant cost of light is the electricity cost, then what you find is that the chip's got to be really cheap. It's got to be something like 30 cents per square centimeter. Which is cheaper even, I think, than most projections that people talk about for GaN on silicon, which itself is intended to be fairly cheap. And that's more like maybe projections that I've seen are more on the order of $10 per square centimeter. So that's going to be the challenge, I think, for LEDs, is that if you care about ultra efficiency, how are you going to get the cost down so that you can drive it at that low power density? Of course, you can go the other direction. You could make use of lasers, and of course, when you cross threshold, then the laser starts to laze. And if you ask, and in this case, this is a simulation of sort of a state-of-the-art, as of a year ago, Osram result. So it's on the order of 30% or so efficient. I think now maybe they're even more efficient than that. But if you operate at its peak, what you find is that because you're driving it so hard, and your efficiency is not bad. Of course, it can get better, but your efficiency is already not bad. What you find is that the areal if you apply the same economics as you did for the LED, the chip areal cost can actually be quite high. I think it can be something like $400 per square centimeter, and you will do okay. And in fact, there's an existence proof. Infrared laser diodes, high power ones that are very efficient, put out a lot of light, they're actually on the order of $150 per square centimeter right now. So in a way, what that means is that there's an existence proof for lasers that in terms of the economics, it's okay. What's not there yet is the efficiency. Of course, it's still not as good as what LEDs are. Alan?
Is that just material cost, or is it factored in the packaging?
That's the packaged cost. Yeah, that's the packaged cost. But it's not the system cost. It's sort of the equivalent of like a lamp, a bulb. eventually going to screw into something else. And there's also a luminaire that itself costs some money. So this is not that. This is just the packaged chip. There is one other thing that you might want to worry about, and that is you're putting out a lot of heat into a little tiny thing. And so there is a heat sink limited chip area, and that heat sink limited chip area will decrease the harder you're driving it until you get to 90% or 95% efficiency. But until you're there, you have to really worry about heat sinking. And what you find is that, in fact, the heat sink limited chip area, if you don't do heroics with heats, you can always do some incredible diamond thing or whatever. But if you don't do that, if you just do sort of normal but good heat sinking, what you find is that the chip ends up being something like 1/10 of a square millimeter in size, which is not very big. But because you're driving it so hard, what you find is that the white light flux that comes out from that chip is still reasonably large. It's like a kilolumen or so. And a kilolumen, as you know, is like about a 65-watt incandescent bulb equivalent. So it's not a bad sort of chunk of light. And of course, if the device improves beyond 30%, or you can drive it less hard, then all sorts of better things happen, and maybe you can get even more than a kilolumen out. So all this is saying is that lasers do appear to be viable from an economic point of view, but there's a lot of work that needs to be done in making them more.
The tipping point, is it pushing the efficiency up of the laser, or is it pushing it to the left? Because,
Yeah.
Which is the right way
Yeah.
to push? I mean, do we push efficiency, or do we push eye threshold?
So is John Bowers here? Larry Coldren? They're not here. Okay, so I can talk about lasers. I can say something about a laser and not get in trouble. So my belief is that it's all about moving to the left. And the reason is that, I don't know about this particular laser, but many of the lasers, especially in the infrared high power lasers, it's really parasitic resistance that gets you. And parasitic resistance, there's other things that come into play too, optical absorption, whatever. Parasitic resistance is a big one. And that really scales as power density. It doesn't scale as power, it scales as power density. And so my belief is that in order to get the efficiency up, you actually have to move to the left. So you're going to end up doing both. You're going to end up moving to the left, and that's going to increase. That won't help other things like optical absorption that you also have to worry about. And for in-GaN GaN lasers, there's magnesium and bad things that absorb P layers. But assuming you can get around that, it's parasitic resistance that's the killer. I don't know. Is that?
I think
There are,
we looked into this hard. I think series resistance, mirror loss, and waveguide loss, they're kind of,
comparable.
they're actually quite
Yeah.
close.
People
you talk to initially say it's all series resistance, but actually if you really look,
Yeah.
it's not.
Yeah.
Pretty evenly.
Especially in in-GaN GaN.
No, in your IR.
Oh, is that right?
I
Oh,
gave you some papers.
okay.
It's actually evenly split.
Okay. Let's see. Okay, so as you can tell, I'm a fan of lasers, and the ultimate would be RYGB lasers, not just lasers that you use in the blue or the violet to pump phosphors. Those are also cool, but RYGB would be even better, and that gives you two things. It gives you, of course, the widest color gamut. Anytime you have monochromatic sources, you get a bigger color gamut. So if you care about chromaticity tuning and all sorts of other things, then it's not a bad thing to have. But the most important thing, perhaps, is that lasers, of course, have lower étendue than LEDs. The effective source brightness is much bigger. So all the downstream optics, everything gets easier using lasers. So easier integration with optics for directing the light. And here you can sort of, this is a, I heard this afternoon all about automobile headlights and things, moving to lasers. And so this is just one example. This is from BMW, and you can see how sharp that nice far field pattern is. And you can imagine, and for automobiles, so that's nice because you're not going to blind your oncoming traffic as well. But even for indoors, for normal illumination, you could imagine tons of situations where you actually care about placing the light where you want to place it, and making it smart and making it more usage efficient than before. So there's all sorts of other downstream advantages to lasers beyond just the economics. Okay, but now, of course, that's easy to say. How how would you actually do that? And so actually, I don't have much to say about this, except that I thought I would just leave with something that I've been thinking quite a bit about, and some of our other folks at Sandy have been thinking about, which is you do have to, so now there's these two things that you have to fill. You have to fill the valley of droop, maybe using lasers. You have to fill the RYG gap, somehow. And extreme nano, maybe, is a route. Okay, maybe not, I don't know. In fact, maybe there is no route. Maybe this just dies because nobody can fill the RYG gap and nobody can fill the valley of droop. That's possible. But if one could, then maybe there's a route here. And I mean that in two different ways. So the first way is in this way, where by extreme nano, I mean quantum confinement in all three dimensions, not just one dimension. And so Larry Coldren and John Byers aren't here, so I can talk about lasers. So here, I'll just remind you of this famous plot of threshold current density versus year, which just shows that quantum wells lasers, of course, are much better than double het lasers. We know that. And quantum dot lasers are, in principle, much better than quantum well lasers, at least in terms of threshold current density, and for the reasons I mentioned. At least part of the efficiency loss is because of high threshold current densities and high parasitic resistance. Quantum dots have other problems, of course, like lack of monodispersity, and so inhomogeneous broadening. And so quantum dots have never really made it big commercially. They have not displaced quantum well lasers, despite their promise, because of these other issues that they, except for narrow, maybe niche applications. But my suspicion is that extreme nano, we're getting better and better at extreme nano. And it's not just coming from the optoelectronics community. As many of you know, for the silicon roadmap, they're on the 14 nanometer node. They're moving fast to the 11 nanometer node, and they're going to eventually get to some of these other nodes downstream. And so even if the optoelectronics community doesn't figure it out, there's a lot of momentum behind figuring out how to get extreme nano and make it really precisely controlled. And if you could do that, then you could move into a regime where not only would you fix the solid-state lighting valley of droop problem, but maybe every single laser at any wavelength would become a quantum dot laser instead of a quantum well laser. That'd be very, very exciting, I think. Okay, then I mean extreme nano in a second way, which is here. And as some of you know, when you get to extreme nano, like 10 nanometers or less or so, you also enter this interesting domain of compliant epitaxy or mechanical compliancy. So for example, if you have a core that's very skinny and you grow a shell around it, if the core is skinny enough, the shell can be made out of a lattice mismatched material, and the core can undergo the deformation that normally, or the it can take up the elastically the strain that otherwise the shell would have had to accommodate. And this is a plot from Ed Yu's work back when he was at UC San Diego, showing the shell thickness that you could grow as a function of core radius. And what you find is that at an 8 nanometer core radius, that shell becomes infinite. You can actually grow anything, or any thickness. And 8 nanometers is coincidentally about the same scale, not quite, it's maybe a little bit bigger, but about the same spatial scale as what you would need for this kind of thing down here. So this extreme nano, and so again, as extreme nano gets more and more under control through just weird, interesting techniques that people are working on everywhere, both in optoelectronics as well, in 3.5s as well as in the group 4 materials. I just have a feeling that there's going to be a lot of interesting stuff going on in this area that might enable both filling the valley of droop and maybe will enable filling the RYG gap. So actually now I'm done. So I just wanted to leave you with, yes, solid-state lighting has made a lot of progress. The best lighting source in the world would be an RYGB laser source. It would be so cool. And if you could do that and make smart and ultra-efficient and even exceed 100% efficiency, there is the potential of huge economic benefit. I mean, we don't know for sure, but there is definitely the potential. And even if that scenario is, let's say, 50% likely, that's still a big motivation. Of course, the Valley of Droop, the RYG gap, those are big deals. But again, even if the solid-state lighting community doesn't solve those, it could be that from the outside there will be some interesting stuff in extreme nano that might enable some of these issues to be solved. So with that, thank you very much.
Wow, it was a great seminar.
No, you guys know all this stuff already, so it's like, it's just,
No, not at all.
and 10 times more. That's
So, any questions for John?
Yes, I have a question about the Spikey spectral. So once you enter the smart lighting, for example, for the communication implication, when we try to modulate some of the spectrums, do you think it will change some of the Spikey spectrum or the results?
see, I'm not quite sure what you're asking. You mean?
So, for example, if we have 4 lasers for the lighting, and we decide to do some of the communication. Like green or blue,
Yeah.
do the modulation, and then say they're going to change the whole results, like the.
Oh, well, so most people that I know about who are thinking about optical communications, they're modulating at such a high speed. You mean, is there going to be interference with the illumination itself? I kind of feel like they're modulating at such a high speed that for the human eye, you wouldn't even notice that it's being modulated. I kind of feel like that's, yeah. But along those lines, I mean, one thing that I've heard people, so you might not want to just use the light for communications, but you might actually want to use it to transfer energy. There are people who are talking about sensors everywhere on the wall, and you don't want to hook them up to power, so they have to absorb power to energize themselves somehow. And through the room lights could be one way. And so one nice thing about Spiky Spectra is that you could tune the light to the solar cell or whatever it is that's in the object that you want to power up. And so you could exactly match them instead of having a broadband illumination source, and then you suffer all the same things that photovoltaics suffer from. Is, well, how do you make super efficiency at all wavelengths? And that's really hard to do. So that's kind of an interesting thing. But yeah.
So, in a situation where you don't want very directional light, is there a big difference in losses from having to diffuse the laser light when compared to LED?
So I don't really think so. I mean, so one of the nice things about lasers is, it's easy to go one direction. It's hard to go the other direction. You can always make the laser worse by diffusing it in some way, and you might have to incur some losses, but it's much harder to do the other. Like if you start with an LED and you want to make it directional, that's like almost impossible. So I kind of feel like you can always go this one. You can always go in that direction.
So you talked about people's preference for the laser versus incandescent or anything. Do people always like the incandescent the best, or can you tune the lasers so that people might like that lighting even more?
Yes. In fact, what we found is that so what we did was when we did the incandescent versus RYGB light comparison, we tuned the color temperature of the RYGB source to be the same, because otherwise people might have a preference for color temperature. So it's the same color temperature. But what we did find was that this RYGB source was slightly more saturated. It didn't have to be more saturated, but the metric we used, Yoshi Ono's, what's his metric called? The color something scale, color quality scale, CQS or something, which actually tends to, and by maximizing that, which is what we wanted, it tends to create a slightly more saturated source. That is to say, you're more at the edges of the color gamut. And so your oranges would look a little bit more orangey. They would look a little juicier and whatever. And whereas that one, it would just look sort of normal. And some people preferred that. They wanted the juicier orange, even if it looked a little bit not quite real, but it looked like really tempting. And whereas other people, they wanted something that was not as juicy, but just kind of looked, So I think it really does seem to depend on the person. It wasn't, But on average, they couldn't, on average, it was sort of indistinguishable in the sense that just as many people liked one versus the other. It was, yeah.
Dan.
Does this illuminant have speckle control, and how does speckle figure into the whole picture?
So speckle's a big deal. So for us, we didn't care about efficiency or anything. We just wanted to make a light source. So we put it through all these diffusers and whatever things, bad things that made it less efficient, but got rid of all the speckle. So here, we that's what we did. But you're right. In a real thing, you're going to have to worry a lot about speckle and whether that means dithering the beam in some temporal but also spatial way or whatever. I think there are ways to do it relatively efficiently, but still, that's definitely an area of engineering that has to be looked at.
Follow up. Do you know, is there any accepted level of speckle modulation depth or fringe visibility that is considered acceptable now? 5%?
I don't know that number. For us, we just did it until we thought it looked great, but I don't know what it was, but yeah.
On the topic of quality of light, in terms of a color rendering index, what would be acceptable for, say, just general light? You mentioned kind of 80% is okay, but obviously there's a trade-off between efficiencies. So what would you peg as like a reasonable number that people would shoot for in a non-special environment?
Yeah, I think in a non-special, a lot of people for 80 to 85 is pretty good. 90 is actually quite good, so you might not normally want 90 unless you're doing something special. But yeah, 80, 85. Is that? Yeah.
I have a couple questions, Jeff. So if I look in the field today, I find solid-state lighting products, almost none of them hit 100 lumens per watt. Right? They're all 60, 70, 80, 90 lumens per watt. Very hard to find a 100 lumens per watt product. So with all the work that you've done looking at efficiency, where do you think GaN on sapphire will saturate? Where do you think we'll be in 2015, 2016, 17 on the predominant technology, which is GaN on pattern sapphire, for efficiency in real lighting products, which includes everything else, includes power efficiency and everything. But if I go buy a light bulb, where do you think we'll end up? Sort of this near term, as we really are tipping now, right? Where do you think the near term will end up?
Yeah. You mean short of going to the more exotic, not exotic, but bulk substrates.
Yes.
Just
what's
what?
Efficiency saturation. Because GaN on sapphire is having a hard time getting much more out of it right now, right?
Yeah.
In my opinion.
Yeah.
But it's struggling.
Yeah. I don't know. I think they should just go to lasers. Just kidding. Just kidding.
I hope you were doing it. We know a lot about blue lasers. We've made a couple here. We know a lot about green lasers. We made some. How do you get a yellow laser?
So I do think that in the long run, well, first, there have been some tantalizing results out of Toshiba and other places where they've got funny interlayers that sort of seem to enable them to get a little further out. There are quantum dot sort of things that seem like they might be able to get further out. But I guess in general, I do think it's in GaN.
You come from the InGaN side.
Yeah, I do think it's in GaN, and I think it's some sort of extreme nano kind of thing that would sort of enable that, But that might take a while. Yeah, it might take a while.
Okay, I've got more questions. Start with Stacy and then two more over here. Stacy.
So in the meantime, when we don't have a yellow laser, I was wondering if you have any opinions about phosphors incorporated with lasers. Do you think that's a route that we should be going
Oh,
down
yeah,
in the meantime?
for sure.
Rather than LEDs?
Yeah, for sure. It'll be blue or violet lasers, just the way for LEDs pumping phosphors. And even then, you still get a lot of the downstream benefits because, of course, the laser can be focused on the phosphor, and so you still get a relatively lower étendue than you could get if you just had LEDs with a phosphor. So there's still many more things that you can do.
Do you think laser phosphor lighting is preferable to LED only lighting?
Laser
Like
phosphor.
LEDs without phosphor is just
Oh, well, yeah, but RGB, but they have the same problem. I mean, you still need yellow, you still need, I mean, so.
But say you can make a yellow LED probably easier than you can make it blaze.
Oh, I see. Oh, okay, okay. Yeah. Okay, so if you could do RYGB LEDs, if you could, and you still can't do RYGB lasers, which would be better? A blue laser pumping a phosphor or a RYGB LED? Huh. Yeah, that's a good question. I don't know. So that, yeah, I don't know.
Okay, we need 2 more questions. If I remember correctly, in the chromaticity diagram you showed, the yellow is pretty much right in between the red and green, almost linear. Yeah, so if those dots are representing the 4, so it seems like you don't need the yellow. I mean, it barely changes the gamut at all. So why do we need the yellow?
Right. So if you're making a display and you're looking at the light itself, then you don't need that. You don't need the yellow. You just need the red, green, and the blue. But if you're using the light to illuminate a scene, and the scene happens to contain something that's yellow, and all you had hitting the scene was red and green, then the yellow thing would look black. So that's not good. And there's enough yellow things in the world around us that it wouldn't be good.
So for a monitor, the 3 would be enough, you're saying for external?
Yes.
You're selling bananas. You should show your scenes with one of those lasers off. That'd be cool.
I should what?
Your fruit basket, you should show with turning off each color.
Oh, yeah. We should do that, huh? Yeah.
You really see the banana disappear.
Then you can see the banana disappear. That's right.
Why you weren't sure that more efficient lighting is a factor of production? I mean, if lighting gets cheaper and if we are saving more energy, then we should be able to use it in many more applications in the developing world. And other people in the developing world, like in Africa and other places, will be able to use it. And energy is a factor of production, so if we are saving more energy. So I am curious why you thought more efficient lighting is not necessarily a factor of production.
Oh, you mean why? Are you asking? Why would you ever believe this scenario is true? Well, I actually don't believe it's true, but you're right. You're right. But this is the standard thing, right? Everybody, in the 1999 white paper, in all the original things, why do we care about efficient lighting? Well, we're going to save energy. That's the most naive, obvious thing to. But you don't think about what the hidden assumption is, and the hidden assumption behind that is that you're going to consume the same amount of light. Otherwise, how could you save energy? And when you think about that, you think, okay, yeah, maybe that can't be true. But a lot of people thought that. Yeah.
If the cost of lighting gets lower, this will reduce the transaction cost of using light in many other applications.
Yeah.
Other people are not able to use light today.
Right. So I think you're right. Almost everybody would agree that in the developing world, where they're lit now the way let's say, the UK was lit in 1900 or whatever, then for sure they're going to march up this curve and they're going to use more light. I think really the argument is in the developed world, in a room like this, a lot of people would say, well, I can't imagine why we would want more light in this room. And they might be right about that, because then you have to think about other applications that are outside the room. But I think maybe you might also say that, which is true, that actually in terms of growth of economies and energy consumption and lighting consumption, whatever, in the next few decades, it is going to be dominated by the developing nations. It's not, the developed worlds just aren't growing nearly as fast as the developing worlds. And so that's really where all the big changes will occur. And they for sure, I mean, it's hard to imagine that they're not in the right scenario. Yeah, that's right.
Okay, Jeff, that was really wonderful. Thanks so much.
Thank you, Jim. Thank you, guys.
That was fantastic.
No, you guys.
It's interesting. Wait,